All right, so we're going to start with where we left off last time, talking about these Grignard reactions here. All right, so everybody take a second and draw me the product of this reaction between a ketone and a Grignard. Okay, cool. So I'm going to actually do the full mechanism here because I want to make a point. All right, first of all, we called our ketone in this reaction is our electrophile. Right? Remember, the electrophile is the electron poor species in your chemical reaction. And our Grignard is our nucleophile, which is the electron-rich species in our chemical reaction. And this kind of principle governs so much of organic chemistry. You have something that has a lot of electrons reacting with something that doesn't have a lot of electrons, okay? In chemistry, we use these electron density maps a lot. So this would be a very simple molecule, HCl, kind of written backwards. All right. This is a very polar bond where the electron density sits on that more electronegative chlorine atom rather than that hydrogen atom, right? Chlorine's pulling electron density away from hydrogen in this bond, a very polar bond. All right, these electron density maps are pretty common where they have this kind of coloration where red, the hot areas mean that there's a lot of electron density, and blue, the cool areas, means that there's not a lot of electron density, okay? So one of the things that we want to start doing in our mind's eye is when we see one of these ketones here, we want to sort of know that this electrophilic center right here is glowing blue, right? It's not got a lot of electron density, all right? Likewise, when we look at our Grignards, remember, because of that metal-carbon bond, carbon's able to take all those electrons away from that magnesium. So likewise, we kind of want to, in our mind's eye, see that carbon right there glowing red hot, right? There's a lot of electron density on that carbon and not a lot of electron density at that carbonyl carbon in my ketone. All right, so my first step in my mechanism is my electrophile, my nucleophile attacking my electrophile. All right, and we said one of the things that makes these carbonyl carbons such good electrophiles is not only are they relatively electron deficient, but they can also accept pairs of electrons without breaking their octet, because as soon as that nucleophile attacks that carbonyl carbon, it's going to kick that pair of electrons up onto that oxygen, right? So it's got this leaving group pair of electrons there, which makes it that much better at accepting electrons from nucleophiles. All right, so now when I'm going to do my intermediate here, we're doing a lot of new carbon-carbon, not a lot of new, one new carbon-carbon bond, but we're adding a lot of carbons to our molecule, right? So things are going to look a little messy, so we need to make sure to be good with counting our carbons. So I'm going to start with the 4 that were originally in my ketone. And I'm going to note that this one here is that carbonyl carbon, or was that carbonyl carbon in my reactant. All right, I've got 2 bonds to draw. One of them is just to that oxygen. It's now accepted that pair of electrons, so it has that negative charge associated with it. And my other one is necessarily now to that Grignard carbon, right? The carbon that I marked in red in my Grignard is going to be on the other side of that new bond. So then I just have to include the 1, 2, 3, 4 carbons around it. I got 2 on either side. It's going to look a little crazy. Cool. And I'm going to make sure to count carbons. Again, I got my 1, 2, 3, 4 in blue, and 1, 2, 3, 4, 5 in red here. Okay. We haven't created our alcohol quite yet in our Grignard reactions. We actually create this, what's called an alkoxide. I've said this a whole bunch. Let's just put it down here. An alkoxide ion. This is just a deprotonated alcohol. Or a hydroxide, but with an alkyl group on there instead of a hydrogen. Okay, an alkoxide ion. All right, and that last step, we got one more step. That would be step 1. Step 2, moving on here, is now when we add that hydronium, that weak acid, your acidic workup step. Okay, and what we're going to have here is just a simple acid-base reaction. That lone pair on that oxygen is going to reach out and grab that hydrogen. All right, real quick, let me get rid of all of my little colors here. All right, if I'm sort of filling in with my mind's eye here, my electron density, what's the hot region of this step here? Where's all that electron density in this step? That oxygen atom, right? Now this is what's glowing red with a lot of electron density, and what's relatively electron poor? My acidic hydrogen, right? That's why hydrogens are considered to be acidic, because they don't have a lot of electron density. Boom. Cool. And so that's how I get my big ugly alcohol product. I just asked y'all for the product, right? But just to do the mechanism here. Again, I think Grignards especially, the mechanism can really help you better understand. And that's really going to be our goal kind of going forward, is looking at these mechanisms and really not treating them as like things we have to memorize, but making sure that we can see and kind of understand why our molecules are moving that way. All right. One last thing with Grignards before we move on. We've now practiced creating our product for our Grignard reaction. All right, what if I asked you to tell me what ketone or aldehyde and what Grignard we could use to create the following alcohol? All right, so there's actually two answers here. You could just give me one of them, all right? But what would be our ketone or aldehyde, and what Grignard reagent will we use to create the following alcohols? All right, like I said, there's sort of two different ways that we could do this, so I'm going to put them both next to one another. All right. If we look back at our previous example, our new bond that we formed was between what used to be our carbonyl carbon and the carbon that was bound to the magnesium in my Grignard. All right, I guess I'll be consistent with my color. So when I look at this molecule here, the one thing I know for sure is that this carbon has a new bond, right? Because that used to be my carbonyl carbon in my aldehyde or ketone. That's why it's got that hydroxyl group on there. But now there's two different ways that I could look at it. I could say, all right, well then this is my new bond. Or I could look on the other side and say, all right, this is my new bond. Either one of those would have been ways to create this aldehyde or ketone. Okay? So if it's going to be the one on top here, that means that these 1, 2, 3, 4 carbons were originally in my, in this case, aldehyde. And the other must be from my Grignard, the other, oops, 1, 2, 3, okay, and importantly that magnesium would be bound to that middle carbon since that's the one that's attached to my carbonyl carbon. Okay. Or I'm going to say, all right, this was my new bond over here. So now that makes these 1, 2, oops. Makes these 1, 2, 3, 4 carbons my aldehyde. And again, the carbon that has the hydroxyl group is going to be my carbonyl carbon. So 1, 2, 3, 4. All right, and that means that my other carbon here is from my Grignard, right? If that's my new bond, and my Grignard is 3 carbons. And I know that this has to be the one that has the magnesium. Boom. Okay, so either one of these would work as methods of creating that, alcohol product using a Grignard reaction. Okay? One of the nice things about Grignard reactions is there's really no preference for either one of these two. Both of these will work just as well. That's not often the case. Sometimes we'll have like a rule about, oh, we need to put the smaller group somewhere, blah, blah, blah. That's not the case for Grignards. Grignards are very, very flexible. There's not any restrictions on what your aldehyde and ketone could be or what your Grignard could be. More substituted, less substituted, all that jazz. Nothing factors into that here. Okay? The important thing is that when I look at that target alcohol, I know that the carbon with that hydroxyl group, it must have been my carbonyl carbon in my aldehyde or ketone. Cool. So yeah, so Grignards are, we're going to see them kind of with a lot of functional groups. They react with all of our functional groups that contain carbonyls. We're going to spend a lot of time on, not only aldehydes and ketones, but also esters and carboxylic acids and all these other functional groups that also contain carbonyls. All right, what we're going to do now, though, is move on to a new type of reaction, what are called oxidation-reduction reactions. All right, y'all would have learned about oxidation-reduction reactions in general chemistry. If you think back to Chem 1B, there was this whole electrochemistry chapter where you talked about oxidation-reduction reactions within the context of batteries, because these are reactions where electrons are being transferred. And that is a big focus on oxidation-reduction reactions in general chemistry. There's this annoying balancing, all that jazz, all right? In organic chemistry, because again, we're talking about such a small subset of elements on the periodic table, we can really simplify our oxidation reduction crap. We don't have to worry about calculating oxidation numbers and charge balancing or any of that jazz, all right? When we say oxidation in organic chemistry, we mean something very simple, which is that we are creating more carbon-oxygen bonds. All right, so again, we're going to simplify things relative to what we learned in our general chemistry. By oxidation, we mean creating more carbon-oxygen bonds. And by reduction, we mean creating more carbon-hydrogen bonds. All right, it's as simple as that. When we oxidize a carbon, we're creating more carbon-oxygen bonds with that carbon. And when we reduce a carbon, we're creating more carbon-hydrogen bonds. Okay? You absolutely could apply the formalism that you learned in general chemistry. Again, it's just overkill. Kind of how we get to simplify all those Lewis structure drawing rules to carbon likes 4 bonds, right? Again, we can simplify things because we're talking about so few elements. Same thing with these oxidation reduction reactions, okay? We're going to first talk about oxidation. So here we have an alcohol, okay, specifically a primary alcohol. Okay. When we talk about primary, secondary, tertiary alcohols, importantly, that oxygen's always going to have just one oxygen-carbon bond, right? That's what it means to be an alcohol. So if I have a primary alcohol, it is because that OH group is attached to a primary carbon. Remember, carbons, we count number of carbon neighbors. This would be a primary carbon because it's got one carbon neighbor. All right, and what we're going to do is we're going to oxidize this primary alcohol. And for right now, I'm just going to use this like O in bracket to represent any generic oxidation reagent, and then we'll introduce specific oxidation reagents here in a bit. Okay, but this, I mean just, whoops, generic oxidation reagent. All right, so if I'm going to oxidize this primary alcohol here, I'm going to create more carbon-oxygen bonds, and I'm going to convert it from being a primary alcohol into an aldehyde. I'm going to turn that carbon-oxygen single bond into a carbon-oxygen double bond. So my primary alcohol can be oxidized to an aldehyde. All right, but this can actually be further oxidized. We can oxidize aldehydes, create one more carbon-oxygen bond. Creating, what would this functional group be? Carboxylic acid. All right, so before we move on, let's just convince ourselves about what we said about our simple definition of what oxidation meant in organic chemistry. We can see that at each step, each oxidation step here, I'm creating more carbon-oxygen bonds, right? So I'm turning my carbon-oxygen single bond into a carbon-oxygen double bond in that first oxidation step, and then adding an additional oxygen to create a carboxylic acid in that second step. All right, cool. So now we're going to take, instead of a primary alcohol, we're going to take a secondary alcohol. All right, and again, what makes this a secondary alcohol is the fact that that hydroxyl group is on a secondary carbon. It's got two carbon neighbors. All right, so based on what we discussed before, see if you can't give me the oxidation product of this reaction here, of this secondary alcohol. So secondary alcohol doesn't oxidize to an aldehyde, but rather to a ketone. One thing to note here, if we go back up, how many hydrogens are there on that blue carbon, my primary carbon? 2. And what about over here on my aldehyde? How many hydrogens are on that carbon? Now just 1. And now how many hydrogens are on that carbon? 0. So notice that in each of these reactions, what I've done is I've replaced a carbon-hydrogen bond with a carbon-oxygen bond. Okay? So because of that, if I have a ketone, rather if I have a secondary alcohol, how many hydrogens are on that secondary carbon? This one right here. Now there's just 1. When I go over here to my ketone, how many hydrogens are there? None. So if I attempt to oxidize this again, I'm not going to get any reaction that occurs. Okay? You cannot oxidize a ketone any further. That's as much as we can do. All right, so then by that same logic, let's take a look at a tertiary alcohol. Okay, this is now a tertiary alcohol. We call it a tertiary alcohol because that hydroxyl group is bound to a tertiary carbon. All right, how many hydrogens are there on that tertiary carbon? 0. So we have nothing that we can replace with a carbon-oxygen bond, so tertiary alcohols cannot be oxidized. All right, so we can oxidize a primary alcohol to an aldehyde. Aldehydes can be further oxidized to carboxylic acids. We can oxidize a secondary alcohol to a ketone, but ketones cannot be further oxidized. And tertiary alcohols can't be oxidized at all. Cool. All right, let's take a look at our oxidation reagents. Okay, we're going to divide the world of oxidation reagents into 2 bins. What we're going to call our strong oxidizers and what we're going to call our weak oxidizers. All right, our strong oxidizers, an example would be sodium dichromate. All right, sodium dichromate is a strong oxidizer. It's kind of an old school one. It's still in a lot of textbooks. Truthfully, chromium is a metal that is associated with oxidation. A lot of our oxidation reagents have chromium in there. It's also terrible for the environment, and so there's been a big push to kind of get away from these chromium-based reagents. They're very expensive to dispose of. Another one that you sort of see in its place is potassium permanganate. That is also a very common strong oxidizing agent. All right, our weak oxidizing agents are both acronyms. All right, we have PCC, which I don't remember what it stands for other than that one of the C's is chromium, because again, chromium is often used in oxidizing agents. The other one I know is named after somebody, Des-Martin pyridine, or DMP, which is again kind of the green alternative to that PCC. PCC is a little old school, not quite used as often anymore because again, very expensive to dispose of, not great for the environment. DMP is kind of the new one that's come on that's started to replace it. All right, so we have these 4 oxidizing reagents here. We group 2 of them in this bin called strong oxidizers and 2 of them in this bin called weak oxidizers. So what's the diff here? All right, so if we look at our oxidation scheme here, if we take that primary alcohol and we treat it with one of our weak oxidizing agents, then we would generate an aldehyde. So this is if we use our weak oxidizer. All right, but if we take that same primary alcohol and we treat it with a strong oxidizer, it's going to blow right through that aldehyde step and give us our carboxylic acid product. All right, so a weak oxidizer will stop at that aldehyde step. A strong oxidizer is going to oxidize it to an aldehyde and then immediately oxidize it all the way to a carboxylic acid. You'll get that fully oxidized product. Just to kind of complete this here, importantly also, if we started with that aldehyde and applied our strong oxidizer, we would also get that carboxylic acid product. All right, for secondary alcohols, doesn't matter. Whether you picked a weak oxidizer or a strong oxidizer, they both do the same thing. They will oxidize to that ketone, and then ketones are stuck, right? They can't be further oxidized. So you're just gonna do whatever's cheaper, whether it's your weak oxidizing agent or your strong oxidizing agent. Either one of them would do the same thing to our secondary alcohol. Okay? Cool. So again, we got these different bins of reagents, strong oxidizers and weak oxidizers. They both do the same thing to secondary alcohols. They oxidize them to ketones. But for primary alcohols, our strong oxidizers will fully oxidize to a carboxylic acid, whereas our weak oxidizers would stop at that midpoint, that aldehyde step. All right, so let's just take a big, ugly functional group, our big, ugly molecule with a bunch of different alcohol groups in there, hydroxyl groups in there. And we want to know what happens if we treat this with our strong oxidizing agent. and our weak oxidizing agent. All right, everybody take a second and give me the product of these two reactions. So importantly, I got these three different hydroxyl groups, but they're not all created equal here. I have one of them down here that's a primary alcohol. I have one in the middle here that's a secondary alcohol. And I have one over here on the left, which is a tertiary alcohol. And these get oxidized differently. If I'm using my strong oxidizing agent, my sodium dichromate, that's not going to touch that tertiary alcohol. Tertiaries can't be oxidized. It's going to oxidize that secondary alcohol to a ketone. And it's going to oxidize that tertiary alcohol completely all the way to a carboxylic acid. All right, if I take that same compound and I treat it with now my weak oxidizing agent, PCC, again, not going to touch that tertiary alcohol. It can oxidize my secondary alcohol to a ketone, and my primary alcohol will be oxidized, but not all the way. It'll stop at that aldehyde step. Be good with my lone pairs here. Okay, so what we can note here is that nothing happens to that tertiary alcohol, right? After both oxidation reactions, it's the exact same as it was when we started. My secondary alcohol does get oxidized, but it doesn't matter whether we use a strong or a weak oxidizer. We got that same ketone product, right? And the big difference is for my primary alcohol with my strong oxidizer that gets converted to a carboxylic acid, and for my weak oxidizer, it gets converted to my aldehyde. Cool. All right. Lastly, we're going to talk about the flip side here, reduction reactions. Okay, our reduction reagents here are sodium borohydride and lithium aluminum hydride. For both of these, there's a second step where you add in this dilute acid. All right. These reagents are called hydrides, so sodium borohydride, lithium aluminum hydride. And that word hydride, when you hear hydride, I want you to think nucleophilic hydrogen. All right, and you're like, wait a minute, hydrogen's going to be a nucleophile? Hydrogen's never a nucleophile. Yes, that is what is so bizarre about these hydride reagents here. They have hydrogens with a lot of electron density that can play the role of a nucleophile, not a role that we see hydrogen play very often. Usually we're talking about proton transfers, where hydrogen is playing the role of an acid, is this very electron deficient electrophile. Now hydrogen's going to play the role of a nucleophile. It's going to be the electron-rich species in our reaction. Okay? For our purposes, for right now rather, at this point in the course, these two are identical. Whichever one you use, you're going to get the same product. Okay? Importantly, the sodium, as sodium always does, is nothing in a chemical reaction. It just serves as a counter ion. So really the important thing here, let's call it our nucleophilic species, is that metal hydride. So whether it's boron with a bunch of with its 4 hydrogens, or aluminum with its 4 hydrogens, all right, these are your nucleophilic species in these reactions. All right, and again, the whole point, the whole shtick, is that in these reactions, these hydrogens are really electron rich in this complex with these metals here. So again, we want to imagine our little hot spot here is this hydrogen glowing red with a lot of electron density. All right, sort of our shorthand for writing this, we're going to look at some mechanism here, would be to write one of those hydrogen metal bonds explicitly and then just group the other ones together, right? Kind of a simplified version of this structure. Same thing over here. And again, we want to imagine that hydrogen glowing red there. All right, that's my electron-rich species. All right, so again, we're going to look at our mechanism for these reduction reactions. They're actually quite simple. And what we're going to do is we're going to start out with a ketone. All right, given what we just discussed with our oxidation reactions, right? A reduction reaction is just the reverse here. So if we start out with a ketone, what do we think we're going to make when we do our reduction reaction? An alcohol. Right? We're going to go the opposite way of what we just talked about here. We got, instead of more carbon-oxygen bonds, we have another hydrogen that we've added, right? To be clear, what's happened in this reaction is, yes, I've replaced that carbon-oxygen double bond with a carbon-oxygen single bond, but importantly, let's note how many hydrogens, rather, were there on this carbonyl carbon? 0, and how many are there on that carbon now? 1. So we've added a hydrogen to that carbon when we reduced it. Okay? And so what we're going to do is we're going to take one of our reagents here. We'll do the lithium aluminum hydride. Right? And we said that these have these nucleophilic hydrogens. So this hydrogen is glowing red hot here. And what is that cool zone on my ketone? That carbonyl carbon is left relatively electron deficient, right? Played the role of a electrophile in those Grignard reactions. Same thing here, okay? Now, importantly, I have to start my arrow on a pair of electrons. My hydrogen atom doesn't have any lone pairs, so I need to make sure to start my electron pushing arrows at that bond. Similar to what we did with our Grignard, right? We got to start our arrow at a pair of electrons. And then am I done with this first step? What am I going to do? I'm going to kick that pi bond pair of electrons up onto that oxygen. All right, so importantly now I've added that hydrogen to that carbonyl carbon. You wouldn't have to draw in the hydrogen explicitly, right? You could have left it implicit, but I think just because we got a new bond here, it's important to show. And my oxygen accepted that pair of electrons, so it has that negative charge. Okay? Just like our Grignards, you will see really, really similar mechanism between these and our Grignards. Right? We have our nucleophile attacking that electrophilic carbonyl carbon. We again create that alkoxide intermediate. And then we have that second step to finish our reaction that involves that dilute acid, our acidic workup. So see if you can't finish this mechanism based on what we discussed previously to get to our alcohol product here. That lone pair on that oxygen is going to reach out and grab that hydrogen, proton transfer to create my alcohol product. All right, so we can reduce we can reduce aldehydes or ketones to create alcohols using one of our reducing reagents. We also can oxidize aldehydes to create, we can oxidize alcohols to create aldehydes or ketones. We can also use a strong oxidizer on a primary alcohol to fully oxidize it all the way to a carboxylic acid. Cool. All right, we're going to continue our discussion of alcohols throughout the remainder of this week.